Alright, so in this tutorial we're going to learn how to draw Lewis dot structures, and we've already learned about charges and how atoms have different charges, positive and negative, and if they have a positive charge then they tend to lose electrons, and if they have a negative charge they tend to gain electrons. And we've also learned about bonds and how they can be ionic bonds, which form between a metal and a nonmetal and involve a direct loss and gain of those electrons, or if they're a covalent bond, which occurs between two nonmetals, and in that case then they share those electrons. But again, the charges somewhat dictate what's going to happen, because if you're an atom that likes to lose, say, 2 electrons, then you would like to find another atom that is compatible to bond with you that would like to gain those 2 electrons. And again, your charges would match up. Also, not only should we look at those charges and we should look at the types of bonds that are forming, but we should also look at electron configurations. And if you recall, electron configurations, our purpose was to make sure that the orbitals, of course, were filled and the subshells were filled as well, giving us a full S and a full P subshell where S had 2 and P had 6. That would give us a total of 8. And our purpose here now is going to be to recall that and take it one step further, which is to make the atoms and the compound, almost all of them, would like to have 8 valence electrons, an octet, so oct coming from 8. And the way we do that, of course, is by either, again, losing or gaining electrons or sharing them. And our purpose, again, is to stabilize the atom and therefore the compound by ensuring that all atoms, with only 2 exceptions that we'll discuss, having 8 valence electrons. So let's get started and discuss Lewis dot structures. And the reason why we call it Lewis dot is because we're going to be using dots that are either just 2 dots or they could be connected into a solid line, and we're going to be using those to help us then determine how we're going to distribute them throughout a particular compound. Alright, so let's take a look here. A solid line, of course, is going to represent a pair of electrons that is bonded, meaning it is a bonding pair. And again, recall when we drew little orbital diagrams of boxes that we had 2 arrows in them, which means that electrons like to be in pairs. So if that pair is involved in a bond, it's a straight line and it is a bonding pair of electrons. And if it's just 2 little dots that are next to each other, that means this is a non-bonding pair of electrons, or as we call them, a lone pair. And again, what we're trying to do is distribute these electrons such that we have an octet, and of course we have a pattern to follow. So let's take a look at these steps, and then we'll try some examples. And we'll go through the steps now, and they'll make a lot more sense when we go through the examples. And you should definitely reference this and go through these steps methodically until you get the hang of writing the and drawing the Lewis dot structures. But it's important not to skip any steps or to go out of order. Alright, so the first thing we're going to do is count the total number of valence electrons that is in the entire compound. And recall that the group number is the same as the number of valence electrons. So if you're in group 1, you have 1 valence electron. If you're in group 2, you have 2. If you're in group 6, you have 6, so on and so forth. And after you tally up the total number of valence electrons in the entire compound, you're going to put them in the bank. And as we begin to build our structure, we will subtract out of the bank until we've used up all of our electrons. So at the end of the day, what we want to do is have an empty bank. We don't want to take any more out, and we don't want to leave any electrons unused, but we're going to use up all those electrons to build our structure. Now, once you have tallied up all the valence electrons in your compound, you can move on to step 2. But it's important to make note that if your compound has a charge, a positive or negative, that means you've lost or gained electrons. So if you have a positive charge, you need to subtract that many electrons out of your bank before you begin drawing your structure. So if you have a positive 1 charge, you need to subtract 1 electron out of your bank before you begin drawing. If you have a negative charge, of course, you'll add that many electrons into your bank. Alright, the next step is to draw your skeletal structure, and you'll simply do that by placing your central atom in the center and then attaching, using a bond, a straight line, all of the other atoms to it, and just building a foundation. Now, what is going to be your central atom? Typically, it's the first atom that is written. So in a compound like CO2, C would be the central atom and the O's would be surrounding it. Once you do build that skeletal structure by putting those straight lines like they are, like this one up here, then what you want to do is, of course, subtract those 2 electrons, because each one of those bonds comes at a cost, and that's a cost of 2 electrons. So for each bond formed, we'll subtract 2 electrons. The next thing we'll do is satisfy the octet of all the surrounding atoms by adding lone pairs. So what we're gonna do is look at each surrounding atom and say, all right, how many electrons does it currently have? Of course, make sure that you're counting the bond as those 2 electrons. That bond is going to count. And then add as many lone pairs, meaning pairs of dots, as you need to make 8. And of course, subtract those from your bank. Now, here's where the 2 exceptions come into play. The 2 atoms that do not want 8 electrons typically in molecular compounds are hydrogen and helium. So they only want 2 because they're very small. So we won't give them 8. Alright, then we'll move on from the outside surrounding atoms and work our way into the central atom. And in step 4, we'll satisfy the octet of the central atom, again using the same method, and again we'll subtract those out of our bank. So step 5, very important not to forget that you're using up those electrons. Sometimes it works out perfectly, and at the end of step 4 we have no electrons left over and all is good, and sometimes we run out of electrons before we can complete step number 4. That means we can't satisfy the octet of the central atom, and in that case we have to apply step number 6, and that is, again, only if you run out of electrons and you cannot fulfill the octet of your central atom. In that case, we have to form multiple bonds. That means a double or triple bond. And all we're doing here is just taking the same number of electrons, but we're rearranging them so that they satisfy the octet of more than one atom. And it's just a way of really economizing our electron and stretching our electron dollars, so to speak, because we've run out of them in the bank. Ideally, we don't like doing this. This is a last resort. You should not be adding double and triple bonds all over your compounds. It doesn't happen that often, and it's not ideal to do that because they're high in energy and less stable, of course, which, and the whole purpose of this is trying to stabilize the compound. But it is better to form a double or triple bond than to leave a central atom without its octet. All right, and last but not least, step 7, and this only applies to if you have a charged compound, you need to draw a bracket and put the charge on the upper right-hand corner to denote that charge. So let's take a look at some examples here. All right, so carbon tetrachloride, which is CCl4. Let's put that on there. And all right, so CCl4 is going to contain 1 carbon in the center and 4 chlorines. So these 4 chlorines, all right, are going to be in group 7, so they'll have 7 valence electrons apiece. So 4 chlorines, it's 7 valence electrons apiece. All right, and that will give us a total of 28 electrons coming from chlorine. It has 1 carbon. Carbon is in group 4, so 1 times 4, it will give us 4 valence electrons. That's another 4. The tally is 32 electrons in the bank. All right, let's start building the structure. Carbon is written first, as you can see here in the formula, so we'll put carbon in the center, and we'll put the 4 chlorines around it using these straight lines. 1, 2, 3, and 4. So 4 bonds will hold the structure together. 4, of course, times 2 electrons is how much they cost a piece. That's minus 8 electrons, and that will leave us with 24 electrons remaining. We'll proceed to the next step, which is to satisfy the octet of the surrounding atoms. And we'll look at chlorine. This chlorine, this chlorine, this chlorine, all 4 of them have a similar structure. So by looking at one, we know it will apply to all the others. Now, each chlorine has 1 bond already. That's equivalent to 2 electrons. So if it has 2 and needs an 8, we only have to add 6 more. So we'll add 6 lone pairs. Here's 1 pair, 2 pairs, 3 pairs, that's 6. We'll add 3 pairs, or 6 electrons to each chlorine, and along with the 2 from the bond, we'll give them each 8. So I'll add 6 lone pairs, or 6 electrons to each of those 4 chlorines, and that will be 24 electrons, and there we go. Those are the remaining 24, and we're left with 0. So that looks good. Now let's complete the last step, which is to look within to carbon. Hopefully it has an octet, because we have run out of electrons and we have no more to give. So let's take a look at carbon. So carbon has 1 bond on the top, 1 on the side, 1 on the bottom. So it has 4 bonds. That means they're each worth 2 electrons, and it's 8. So it definitely has an octet, and we are in very good shape because we have no electrons left, but we've done what we needed to do. All right, so let's take a look at an example where we have some hydrogens. Remember, again, those need only just 2 electrons, and also this particular compound has a charge. So this has a couple of twists in it. Let's take a look at those. All right, ammonia, which is NH4, contains 1 N. N being in group 5 will give us 5 electrons, and 4 H's, and each H being in group 1 will give us 4 electrons there, and that's a total of 9. But notice that it has a positive charge, positive 1. That means we'll subtract 1 electron, and that will give us 8 electrons total in the bank that we can use to build our structure. Again, we will put the first element, which is nitrogen, right there in the center. We'll put all 4 hydrogens around it using bonds, so 1 bond on the on each side, 1 on the top, 1 on the bottom, and that will give us the 4 bonds. And those bonds, again, come at a cost of 2 electrons. So we have 8 electrons total to use, and we've already used them all up just by drawing our skeletal structure. So hopefully everything will work out because we've already run out of electrons. Let's take a look at, again, the surrounding elements first. Okay, each hydrogen, remember, requires only 2 electrons. So there's got 1 bond, and that's 2 electrons. So just by having that 1 bond, each hydrogen has its 2 maximum electrons, and we don't have to worry about them. All right, so that's one hurdle passed. Now let's take a look at nitrogen. Hopefully this has an octet because, again, we have no electrons left. Well, nitrogen has 4 bonds, and 4 times 2 is 8. So nitrogen luckily also has an octet. So again, we're in good shape. We don't have to worry about forming multiple bonds. We've used up all the electrons, but no more, and we have satisfied the octet of all of our elements. The last step, of course, since this did have a charge, is to put the bracket around it and put the charge on around the bracket. So last of all, let's take a look at this carbon dioxide example, and this one, of course, has a multiple bond being formed, and the reason for that is because we will run out of electrons. So again, let's take a look at the formula, which is CO2, 1 carbon, group 4 is 4 electrons, 2 oxygens, they're in group 6, 2 times 6 is 12, and we add those up and we end up with 16 electrons. So we'll put carbon in the middle, each oxygen on one side, and if we actually take it back to its original form before we've added the multiple bonds, like so, this is what we get as a skeletal structure. So by putting these 2 bonds on either side of carbon, I've used 4 electrons, and by taking those 4, I have only 12 left. Alright, so if I have 12 electrons left, I need to satisfy the octet of my surrounding elements, which is oxygen. This oxygen has 2 electrons, and this one has 2 because of the bond, so each of them needs 6 more, right? They have 1 bond, that's 2 electrons, and they need 6 more to make 8. So I'll add 2 on the top, 2 on the bottom, and let's say 2 here on the side, and there's our 8. So 2, 4, 6, and 8. And we'll do the same over here, and that'll have 2, 4, 6, and 8. Well, by adding 6 to this oxygen and 6 to that one, there's my 12, all gone. I'm left with 0, which is still okay, but let's look within the center to this poor carbon. Carbon has 2 bonds, which is 4 electrons, but it needs 4 more to get an octet. What happened? I don't have any more here in the bank. So what I'll do is I'll take away that pair, I'll take away this other pair, and instead of having just 1 bond, I'll make this one a double. And what will happen is oxygen is no worse off. It still has 2, 4, and then 6 and 8. And the same on the right. But what happened to carbon now? It's got 2, 4, 6, and 8. And so we have satisfied the octet of all atoms using the same number of electrons by forming a multiple bond.